Hey, welcome back to Calculus. In this first part of section 4.3, we're going to see how we can use the first derivative to determine the intervals over which a function's outputs are increasing or decreasing. At the same time, we'll be able to classify any critical values of that function as either local minimum or maximum. That is, we'll be able to find and classify all of its local extrema. So you can see the objectives there. We're going to start off by looking at this increasing decreasing test. It answers the first question: where is the function's outputs increasing and where are they decreasing? The first derivative test is a nice way to classify the local extrema, and we'll actually be able to do all of this work with a nice sign diagram for the first derivative. Yeah, so we've seen sign diagrams before back in chapter 3 when we were analyzing the motion of a particle along a line. We're basically going to use those sign diagrams in the same way here to make inferences about where a function is outputs are getting bigger and where its outputs are getting smaller. So you can see I've got the fundamental problem kind of written there. I just want to emphasize that we're always asking what the outputs are doing, getting bigger or getting smaller, but we always ask it as the inputs increase. So it's very important to keep that in mind, that we're reading the graph left to right along the x-axis, yeah? The inputs are along the x-axis and they increase as it moves from the left to the right. So we're asking the question, what are the y values doing? The outputs on this curve, are they getting bigger or are they getting smaller? But it's always as the inputs get bigger. So I'm going to switch over to Desmos here just for a second, just to emphasize that. Now we've got a picture ready. We're going to come back to this picture in a static way in a little while here, but you can see a graph of a function. I've got it drawn there. Don't worry about what the formula is, but I'm showing you an input. And I'm going to start increasing that input. I always read these graphs left to right. So as that input coordinate starts getting bigger, you're going to see in the picture, there's the corresponding dot on the curve. And then I'm just plotting the output coordinate on the y-axis. So you can see right now that that output, it's dropping. Yeah, this function is decreasing. The function is decreasing because the output coordinate is getting smaller. The input coordinate is always increasing. All right, so now we're getting to that little low point right there, and now the output's starting to rise. So the function is increasing, okay? Still increasing, and now it's starting to decrease. I'm watching that thing on the y-axis, it's getting smaller, right? That function is decreasing, it's gonna turn around right there, and now it's increasing. And as the input continues to increase, it looks like that output just increases indefinitely. So again, the purpose of doing this little demonstration at the beginning of the lecture is to remind you that when I'm talking about a function increasing or decreasing, I'm always talking about what its outputs are doing. And in particular, I'm talking about what its outputs are doing as its inputs increase. Okay, it's important. As the inputs increase, as you read the graph from left to right, what are the outputs of the function doing? Are they getting bigger or are they getting smaller? Okay, so let's start by stating this increasing, decreasing test. I don't think this will even feel very new. We've been talking about this a lot in our applications of derivatives. We've said when derivatives are positive, the function's values are getting bigger. When they're negative, they're getting smaller. So that's exactly true. That's what this increasing, decreasing test says, that if the first derivative of a function on an interval is always greater than 0, then that function is increasing on that interval. If the first derivative of a function is negative on an interval, then that function is always decreasing on the interval. So I personally like this test. I think it's an example of mathematics being kind to us because it's kind of easy to remember. First derivative positive, something's getting bigger. First derivative negative, something's getting smaller. Positive I sort of associate with bigger and negative with smaller. So it's kind of nice to remember it that way. I'm not going to write a formal proof of this, this increasing, decreasing test, although it is a chance. I'm kind of bypassing a chance to use our mean value theorem. The mean value theorem occurs in the book right before this because the proof of this test actually follows from that. Just to give you some quick idea, if you had two inputs, say D is bigger than C, and the function weren't increasing on the interval, say, containing C and D, yeah? So if f isn't increasing, then what could I say? There would be 2 points, say C and D, where f of D was less than or equal to f of C. Yeah, so that I have one input D that's bigger than C, but the output isn't bigger. So that would mean that f isn't increasing. Well, then the average rate of change, f of d minus f of c over d minus c, would be less than or equal to 0. And so the mean value theorem would say that the derivative, f, has to be less than or equal to 0 somewhere between c and d. But if the derivative is always positive, that can't happen. Yeah, so that's just a sort of sketch of the proof of this. The increasing decreasing test, if you like, if you don't want to even have any detail, it follows from the mean value theorem. Yeah, if the function ever decreased, then you could find a negative average rate of change. If the function ever increased over an interval, you could find a positive average rate of change. The mean value theorem says that those averages have to be the instantaneous at some point. Okay, let's look at an example. Let's look at an example. Brought that function back from the Desmos screen. Now you can see its formula. It's a fourth degree polynomial, 3x to the fourth minus 4x cubed minus 12x squared plus 5. And the question is, determine the intervals over which f is increasing and decreasing. All right, we looked at the animation in Desmos to give you an idea of what I mean by that. So here I'm just kind of color coding those intervals in this picture. So I've got f of x drawn, the axes aren't marked, but the function is increasing over any portions of the curve where, as I read the inputs left to right, remember the input is always increasing, then the outputs are getting bigger. So the portions of the curve over the parts of the x-axis that I've highlighted in yellow have that property, yeah? Those are the intervals that x moved through in the increasing direction for which the y-coordinate was getting bigger. And you can see that on the graph, right? The y-coordinate is getting bigger on that portion of the graph. The y-coordinate is getting bigger on this portion of the graph as the input increases. If you look at the picture as the input is decreasing, everything's going to switch. So always read the graph left to right. The blue intervals just indicate where the y values are dropping. Yeah, if you take x in that blue interval or this blue interval, the y values over such intervals are getting smaller. And basically the question I'm trying to ask is, well, what are these x values where that's changing? What is this x value where it stopped decreasing and started increasing, vice versa, and so on? Yeah, so I want to know those x values so I can write down the intervals. So the strategy is to make a sign diagram for f prime. All right, so let's compute our derivative. Try to make it so that we fit this stuff in here. So f prime of x, you can stop the video, I hope, and compute this derivative without me. It's 12x cubed minus 12x squared minus 24x is the derivative. But I'm interested in more than just what this derivative is. That's a perfectly fine form to put it. But I want to know, well, where is this derivative positive? Where is it negative? Well, it's a continuous function. So the intermediate value theorem, one of our tools, says that we should just find where it's 0. Because if you know where a continuous function is 0, then you can just check in between to see if it's positive or negative. So if I want to know where a function is 0, I want to factor that function, yeah? So I'm going to continue to do this. The algebra is motivated by what I'm trying to do. I want to factor this thing because I want to know where it's equal to 0, and I can't see it in this form. I can see that I can factor out a 12x. Every term is divisible by 12x, so if we start by doing that, we at least reduce the size of our problem here. It would factor into 12x times x squared minus x minus 2. And then that quadratic expression also factors, doesn't it? What would it factor into? It would factor into x, say, take away 2 times x plus 1. Okay, so now in that form, I can see I'm setting this equal to 0. I want to know where it's equal to 0. So I'm just making this an equation. I've got my derivative and I'm setting the derivative equal to 0. And in this factored form, I can see that there are precisely 3 solutions. That the 3 values of x that make that 0 are x equals 0, x equals 2, and x equals negative 1. So there are precisely 3 values of x that make that function equal to 0, the derivative, f prime, equal to 0, and they're those 3 values. Okay, so now I'm going to make a little sign diagram for the first derivative. Just going to draw a number line down here. It's just a schematic. I'm going to write f prime over on this side to remind myself what this sign diagram is for. And on that number line, I'm going to mark the 3 values that we just found. -1, 0, and 2. You don't even have to mark them to scale, but I kind of like to. And those zeros that I'm writing there are just reminding me that f prime is 0 at those three values. So I'm writing my x values down below. I'm writing the f prime values up above. Okay. And now either by selecting a sample point, so what do I mean by that? In each one of these three intervals, you need to choose a number. Four intervals, pardon me. Four intervals, you need to choose a number. For example, maybe on this one, I might pick the number -2, okay? And then you have to determine, is f prime of -2 a positive number, or is f prime of -2 a negative number? Whatever the answer is, it would be the same for any number in this entire interval. That's where I'm using the continuity. Testing the value at a single point will tell me the sign over the entire interval, because a continuous function can't change sign without being 0. And we know precisely where it's 0. These are the three possibilities for it to change sign. Okay, so you need to select numbers. And here there's no whole number. You might have to pick a number like -1/2. Here you could pick the number 1. Here you could pick the number 3. You can pick any number in the interval, and you have to test it. Okay, so if I was going to test this f of -2, f prime, excuse me, f prime of -2, I need to give myself a little bit of room here to do it. So f prime of -2, and let me show you where I'm looking when I'm going to compute this. I'm looking right there. And I'm actually not even really going to do out the detail. You can just take a calculator out and compute f prime of -2, do it in your head. It's no problem. But I don't really care what f prime of -2 is. Yeah, I just care, is it positive or is it negative? So really what I'm doing in my head here is I'm going, well, f prime of -2 is 12 times -2 times -4 times -1. Yeah, I'm just looking at these factors. I'm putting in a -2 right there. -2 is -4. -2 plus 1 is -1. And now I'm just counting. That's a positive times a negative times a negative times a negative. That's a negative number. Yeah. So that's how I'm going to conclude that this has minus signs over that interval. That entire interval, the function's derivative is negative because it was negative at one value. And I'm just trying to give you a hint that you don't really have to evaluate f prime. Like here, if I take a number, say between -1 and 0, I don't want to plug a half into this thing or -1/2 and do a bunch of arithmetic. I don't really care about the value. I just care about its sign. So here's how I'm thinking about this. If you take a number that's between -1 and 0, well, since 12 is always positive, I'm just going to look at the three variable factors. In this factor, that number would be negative. You subtract 2 from that number, it's more negative. But if you add 1 to it, you get a positive number because the number was bigger than -1. And a negative times a positive is a positive. So this function, f prime, will be positive throughout that entire interval. All right, and so on. I'm going to allow you stop the video and check the signs. I'm just going to write them now. I'm not going to make this thing long by doing out the details, but if I choose a number between 0 and 2, I can just kind of talk you through it real quick. That number would be, this would be a positive factor. The middle factor would be negative, but the third factor would be positive. And if you have one minus sign, the result is negative, I mean. On the right of 2, all three factors would be positive, so the result will be positive. Okay, so you can check specific points. You can do that at your own speed, or you can just think about the signs. All calculus students fall into a wishful thinking trap that you just have to do this one side and then they just alternate minus, plus, minus, plus. That's not true. In general, these signs can go negative, 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 positive, positive, negative, and any four possibilities are true. So you have to check every interval, okay? But now we're in a position to answer our question. I'm going to try to keep a lot of this visible, but this labeled sign diagram for f prime together with the increasing decreasing test tells me how to answer the question. Yeah, because I can see where the derivative is positive, I can see where it's negative. So let me just write my answer in the form that I'm going to expect you to write your answers in interval notation. So I'm going to write something like this function f is increasing on the intervals, well, where are our plus signs? The leftmost one is the interval from -1 to 0. Those are input ranges, yeah? So I'm not writing points, I'm writing x values. That's the interval, starting with x equal -1, ending with x equals 0. You never include the endpoints. So it's increasing on that interval, but then together with, remember our mathematical union operator, together with the interval that starts at 2, and well, it has no upper bound. So the way we denote that is with that infinity symbol. So those are the intervals over which f is increasing, okay? F is decreasing on what intervals? Well, all the way from -infinity to -1, together with 0 to 2. So those are intervals, not points in the plane, intervals, all right? So if I tried to squeeze down just a little bit so we can see all this, now we've kind of analyzed this function nicely. We know precisely what this x value is. That's the x value -1. It was sort of clear, I think, that that's the origin, but that's x equals 0, and this must be x equals 2 over here, yeah? So those are the precise cutoffs where that function is decreasing, then increasing, and so on. Nice. So that's kind of what I want you to learn how to do in this section, is to organize a sign diagram for the first derivative and then know how to extract the information out of that sign diagram to write down the answers to these questions. Where is something getting bigger? Where is something getting smaller? It's always where the derivative is positive and where the derivative is negative, respectively. Okay, so you might want to pause and let that soak in a little bit here. I'm just going to keep going and say that, I can kind of notice something else. Uh, um, these numbers that make the derivative 0 there, or undefined, this one had no undefined values, but those are the critical numbers. You remember that piece of vocabulary? These are the critical numbers for f. And remember, we have a theorem that says if you're looking for extrema of a function, you should look at the critical numbers. You should look at where the derivative is 0 or undefined. And this sign diagram kind of tells us what's going on at each one of those critical numbers. If you're looking at the graph, you can clearly see that there's, say, a local minimum at x equals -1. Yeah, a local minimum there at x equals -1. That's the smallest y coordinate nearby. Nearby x equals -1. How does this sign diagram tell us that? Well, the sign diagram tells us that in the following way. As x approaches -1 from the left, our function was decreasing. Yeah, the derivative was negative. But then as x continued to increase past -1, the function started increasing. Well, if a quantity stops decreasing and starts increasing, it must have a local minimum there. So encoded in the sign diagram, the fact that the first derivative was changing from negative to positive, I could have told you that that was a local minimum at x equals -1 without that picture, yeah? Because if something stops decreasing and starts increasing, it must have bottomed out. It must have turned around. Likewise, you can continue. If you look at the sign diagram here, I've already got the increasing arrow on -1 to 0. From 0 to -2, it started decreasing. Well, if a function stops increasing and starts decreasing, it must have a local max. Always concluding local here. This idea that I'm hinting around won't ever tell me about global extrema. That's a separate question. But there has to be a local maximum. You can see it in the picture. And it's a local maximum because the function stopped going up and started going down. Likewise, if we complete the sign diagram, it starts increasing after 2, local min. So in making that sign diagram for the first derivative, we have the opportunity to answer all of the questions posed in the objective of the lecture. Yeah. The sign diagram, first of all, tells me where the function's derivative is positive and negative. That's the increasing, decreasing question. And in the case that the function ever changed from decreasing to increasing or vice versa, we get an extrema there. And that's encoded in the sign diagram. Cool. All right. So let's state that formally. I'm going to scroll down I was pessimistic. I left myself a lot of room. But what we were just talking about is the second result from this first part of the 4.3 section. It's called the first derivative test. Okay, so what does the first derivative test say? It says that if you have a critical number, good or bad, so remember what that means. That you have a critical number. It means that the derivative f is either 0 there. Oops, sorry about that. F prime of c is equal to 0, or f prime of c is undefined. In either case, we'll call it a critical number, all right? And the first derivative test says, well, there's some cases. There are some cases. It says that if f prime, not f, but if f prime is changing from a positive value to a negative value, then you have a local maximum. So that's what you're seeing here in the leftmost picture. And what I've drawn below it is a little picture of what the sign diagram would look like there, yeah? If I went back to my scheme before, if the first derivative is positive, the function is increasing. If the first derivative is negative, it's decreasing. Well, that's what a little local maximum looks like. Nearby the value c, the graph of f has to look like this. It had to have peaked out. Conversely, if the first derivative changes from negative to positive, then you have a local minimum. That's this second picture from the left. The sign diagram would look like derivative switching from negative to positive, right? So something has stopped decreasing and started increasing. That's a local minimum. But there's two other possibilities when you have this critical value. Here, I wrote 0 everywhere for my critical value. It could be undefined as well. But the first derivative could do something like this. It could be positive, hit 0, or be undefined, and then stay positive. All right? In that case, you don't get an extrema, right? What was the function doing? It was increasing, leveled off, and then continued to increase. Okay? You don't have an extrema there. Or the last possibility is that the derivative was negative on both sides of your critical value. So what does that mean? That means that the function was decreasing, it leveled off, and then it continued to decrease. You don't get an extrema. All right? So that's the first derivative test, and we've already used it. We already used it. I'm going to scroll back. Basically, when I was filling out this sign diagram with those blue arrows, I was using the first derivative test. I was classifying those extrema using the first derivative test. All right, so really the increasing, decreasing test and first derivative test, you use them at the same time, and in particular, you do it with a sign diagram for your function. Let's look at another example. One more computational example here, and then I'm gonna do something a little bit conceptual, and then I'll turn it over to you to practice this stuff in your activity and your homework problems. So I'm going to take a logarithmic function. It's x squared times log x. It's defined only for x between 0 and infinity, because the logarithm function's domain is that interval, positive numbers only. And I want to do the same thing. I want to determine the intervals over which f is increasing and decreasing. I want to find and classify all the local extrema. Okay, you're looking at a graph of the function there. So we can kind of see, it looks like it starts off decreasing and then somewhere, that's the question, is where, right? These y values start off dropping. Somewhere around right there, it looks like they bottom out, and then it looks like they increase after that. So I want to be able to say, well, where exactly is that? And is this picture telling us the truth? Maybe there's some detail around the origin here that we can't see because of scale or something. Okay? So process, if you're a step person, you start these problems by carefully computing and simplifying as much as possible the first derivative, because we need to know where it equals 0 and where it's undefined. Okay, so f of x is written up there. We're going to compute its derivative. I hope you'll stop the video and compute it without me. If you're still listening, use the product rule. F is the product of x squared and log x. So let's do it. If we differentiate the x squared part, that's 2x times log x undifferentiated, and then x squared undifferentiated, derivative of logarithm. Do you know it? It's 1 over x. And I'm going to start simplifying that a little bit because I want to know where it equals 0. So x squared times 1 over x is x. It looks to me like all I can do is factor out an x out of that expression. And as soon as an expression is completely factored, it's an appropriate time to say, well, where's this thing equal to 0? I don't have to, yeah, so where is it equal to 0? It's always defined. There are no bad critical numbers because of our domain restriction. We're only allowing x to be positive, so this logarithm term down here is defined for all such values of x. All right, so the two solutions to this equation, well, one of them would be x equals 0. It comes from this factor. The other one is that the other factor is 0, right? So it could be the case that 2 times the log of x plus 1 is 0. And we have to do just a little bit of algebra there. That's equivalent to the log of x being minus 1/2. And if we exponentiate both sides, that's equivalent to x being e to the minus 1/2, or if you prefer, 1 over the square root of e. You can get a decimal approximation for that if you want to, but I'm going to leave it as 1 over the square root of e. It's some number between 0 and 1. Okay, good. So we just have 2 critical values, but actually that's sort of a misspeak. We don't really have a critical value x equals 0, again, because x is not allowed to equal 0. So we just have one critical value. So when we go to make our sign diagram for f prime, it's always just a number line. I like to label it f prime. There's just one value that we have to mark on here, 1 over the square root of e. 1 over the square root of e is the only value of x, and it makes our first derivative 0. Yeah? We have to remember that our function is defined only for positive x. So this left-hand interval is not unbounded. It stops at 0. The right-hand one is unbounded. X can go all the way to infinity. All right, so I'm going to leave it to you to check the details here. But if you choose a number between 0 and the 1 over the square root of e, well, then the logarithm of that number is going to be less than minus 1/2. So 2 times it will be less than minus 1. And when you add 1 to that, you're going to get a negative number. So you can check this, check it with a calculator. But if you choose a number between 0 and 1 over the square root of e, get a decimal for it if you need to, plug that number into your derivative back into this expression, then I claim that the value of that is going to be negative. You could also plot the derivative. There's lots of ways to answer this question. So come to me in my office hours if you're not clear, but the question you're trying to answer is, for x between 0 and 1 over the square root of e, is the derivative positive or negative? There's lots of ways to do that. I know it can't switch sign in between because I know where all the critical values are. All right, you can also verify that if you take x to be bigger than 1 over the square root of e, then the first derivative is positive. Okay, so I can write down my intervals of increase, decrease now, and I can also tell you what's going on, because if you've stopped decreasing and started increasing, you must have a local minimum. There's a local minimum at 1 over the square root of e. In this case, that local minimum is the only extremum, so it actually has to be a global minimum as well, but that's a separate question. And then let's write down our interval as our increase, decrease answers. So from this sign chart, don't have a lot of room to do it, so we better squeeze it in. So f is increasing. Can you write it before me? On the interval from 1 over the square root of e to infinity. F is decreasing on the interval from 0 to 1 over the square root of e. Okay, and we have a local minimum at x equal 1 over the square root of e, no other extrema. So we found and classified all the extrema. We have specified where the function is increasing and decreasing. Okay, one more kind of conceptual example, not a computational. I hope you're going to practice that a lot on the activity problems and the problems in your homework. You have to repeat this process. You'll get more and more algebraic experience as you do, but that's your practice, that's your work. Here, I want to just do kind of a conceptual problem. So I've drawn a picture of a function. It's not f of x, it's f prime of x. Very important. You're looking at a graph of the derivative. And then I'm asking you questions about f, right? So this is, I'm going to just try to emphasize it in my voice. This is going to be kind of a lot of our work. I'm trying to use the derivative to give me information about the function. And it's very important that you keep which one is which straight, okay? So you're looking at a graph of the derivative, but I'm asking questions about f. I'm asking where f is increasing and where f is decreasing. I want to classify the local extrema. Well, I've been trying to talk you into, you make sign diagrams to do that. You make sign diagrams for the first derivative, right? So looking at that picture up there, can you tell me the critical values? When is f prime equal to 0? Which values of x? It looks like there's two of them, at x equals 1 and x equals 5. Those are the two values of x that make f prime 0. It's where it's crossing the axis. Yeah. So I'm going to mark those two numbers on my sign diagram, 1 and 5. They make f prime 0. Looks like f prime is defined for all values at least between 1 and 6. Okay. Let's say here, for purposes of this problem, that the domain of this function is just the numbers between 0 and 6. So in our sign diagram here, we'll throw in endpoints. You always need to know that, because for the right and leftmost interval, you need to know, like, well, do they go all the way to infinity or do they stop somewhere? So I'm saying, let's say they stop somewhere. And then between 0 and 1, can you look at that picture of f prime? I don't have anything to plug into. There's no algebra to do here. But the y coordinates of the graph of f prime are above the x-axis for x between 0 and 1. Yeah? So the first derivative is positive there. Between 1 and 5, all those y coordinates are below the x-axis. And then between 5 and 6, they're above it again. All right? So we can answer our question. F is increasing. F, not f prime. F is increasing on the interval from 0 to 1. I never include the endpoints because you're not increasing or decreasing at a point, together with the interval from 5 to 6, pardon me. And it's decreasing on the interval from 1 to 5. Okay, good. So the last thing I'm going to say, because I'm asking you to do some problems like this in your homework, and some of you who are still watching this might be confused right now. You might be looking at this graph going, what are you talking about? Like from x equals 2 to x equals 3, it's increasing, right? Those y coordinates are getting bigger, and that's true. Those y coordinates are getting bigger from 2 to 3, but those y coordinates are not on the graph of f. They're on the graph of f prime, all right? So f prime is increasing from 2 to 3. Yes, it's true, but I was asking questions about f, okay? So very good. I hope that's helpful for you, and thanks for listening.